Tonight, we're traveling back billions of years to a version of Earth that looked complete, yet nothing like the world we know. This was already an old planet. Oceans covered most of its surface. Continents were forming, breaking apart, and drifting again. And life, though invisible to human eyes, was already at work. For most of Earth's history, the sky above was not blue. There was no oxygen to breathe, no ozone to soften the sun. The air followed rules no human has ever lived under. Sunlight passed through unfamiliar gases, interacting with chemistry rather than comfort, and producing colors determined entirely by physics. The oceans reflected this same uncertainty. Their color was not fixed because it depended on who lived at their surface. Long before plants turned the land green, other organisms ruled sunlight. They used pigments, unlike chlorophyll, absorbing and reflecting colors modern ecosystems no longer allow. Some scientists believe these ancient seas may have appeared tinted in deep purples or reds, not because the water changed, but because life had. At the same time, the sun itself was dimmer, a younger star shining through thick methane haze produced by early microbes. That haze filtered light unevenly. Blue wavelengths scattered away before they ever reached the ground. Sky, sea, and life were not evolving separately. They were reshaping one another. Tonight, we gently explore how scientists reconstruct lost worlds using chemistry, fossils, light, and living analogs. But before we begin, I'd love to know where in the world you're listening from and what time it is there. If you enjoy these gentle journeys into Earth's distant past, please do consider leaving a like and subscribing to the channel. Now, take a deep breath, let your shoulders relax, and together, let us step softly into a version of Earth that no longer exists. Earth's familiar colors feel permanent only because they have remained unchanged within human memory. Beneath that calm surface, color is not a property of the planet itself, but a momentary outcome of invisible interactions. The sky appears blue, not because it contains pigment, but because incoming sunlight fragments as it moves through gas. Shorter wavelengths scatter and linger, washing the overhead world in blue, while other colors pass through more directly. The sky becomes a soft mirror of motion rather than a painted ceiling, shaped by molecules too small to be seen, yet constant enough to guide every dawn. The ocean borrows that color, but never entirely owns it. Water absorbs light unevenly, drinking in reds and warmer tones, while allowing blue to travel deeper and return to the surface. On calm days, the sea reflects the sky above, extending the color downward until horizon and atmosphere blur together. Yet the ocean's blue is also biological. Countless microscopic lives drift near the surface, their chemistry tuned to absorb certain wavelengths and scatter others. Their presence subtly reshapes the light, tinting water that would otherwise lean toward darkness. The ocean becomes an archive of both physics and life, layered together in gentle motion. When either layer shifts, the illusion breaks. Change the composition of the air and the sky's color alters its tone, sometimes fading, sometimes deepening, sometimes wandering into unfamiliar hues. Adjust the chemistry of the sea or the organisms living within it, and the surface responds quietly but completely. Color follows chemistry with unwavering loyalty. It does not resist, mourn, or remember, it simply obeys. The planet's appearance remains flexible, waiting for the conditions that define it. In this way, Earth's modern palette exists not as destiny, but as timing. The balance between atmospheric gases and ocean life happened to settle into harmony during this brief chapter of the planet's long story. Nothing about blue skies or blue seas was promised in advance. They emerged because chemistry aligned with biology, and light found a path that favored these tones. Had the balance tipped slightly earlier or later, the world would glow differently under the same sun. This quiet rule governs the entire planet. Alter what fills the air or what stirs the water, and Earth's surface responds without ceremony. Color becomes a record of internal change, written in light rather than stone. The planet does not hide its transformations. It displays them softly across sky and sea, waiting for attentive eyes to notice what has shifted. Long before oxygen reshaped the surface of the planet, Earth existed under an atmosphere that would feel deeply unfamiliar today. The air was thick with gases released from volcanoes and the slow chemistry of stone and sea. Nitrogen drifted quietly beside carbon dioxide, methane, and sulfur compounds, forming a sky that neither supported fire nor welcomed lungs built for the present age. This was not a world lacking life, but one built on different rules, where survival followed paths now mostly forgotten. Life learned its earliest rhythms in this air. Microbial communities flourished in places where water met rock, drawing energy from chemistry rather than breath. They metabolized metals, sulfur, and light, weaving themselves into mats and films that clung to shallow seas. Oxygen was unnecessary and even hostile to many of them. They evolved defenses against it rather than dependence on it, shaping ecosystems that thrived in stillness, heat, and chemical gradients. The absence of oxygen did not limit life, it defined it. The sky above reflected this difference with quiet honesty. Without oxygen and without an ozone layer to filter incoming light, sunlight interacted with the atmosphere in unfamiliar ways. Certain wavelengths passed through easily, while others scattered or were absorbed by gases that no longer dominate the air. The result was not a stable blue dome, but a shifting canopy whose colors depended on chemistry rather than habit. Haze, tint, and tone varied with volcanic pulses and atmospheric balance, sometimes muting the heavens, sometimes staining them with unfamiliar hues. This instability extended across the planet. The sky was not yet a reliable feature, and neither was the sea's appearance. Light entered the water carrying a different spectral balance, influenced by the air above and the substances dissolved below. Minerals and early organisms altered how light moved and returned to the surface. Color followed conditions moment by moment, sensitive to slight changes in chemistry. Nothing about Earth's appearance had settled into permanence. Through this long stretch of time, oxygen remained absent, not because it was impossible, but because it had not yet found its place. The planet functioned smoothly without it, cycling elements through rock, water, and living cells with patient consistency. The atmosphere breathed in its own way, exhaling through eruptions and erosion rather than forests and plankton. Earth did not lack balance, it simply balanced differently. In this ancient world, the idea of a permanent blue sky would have felt meaningless. Color was not fixed, and neither was the air itself. Earth's surface was already fluent in change, long before oxygen began its slow and transformative rise. In Earth's earliest chapters, the sun rose with less intensity than it carries now. Its light arrived thinner, stretched across space from a star still settling into its long adulthood. Days were illuminated gently rather than brightly, and the energy reaching the surface carried a softer weight. This quieter sunlight shaped the planet in subtle ways, influencing how warmth gathered and how color revealed itself across land, sea, and sky. With less energy arriving from above, light interacted differently with the atmosphere it entered. Shorter wavelengths scattered less efficiently, while longer wavelengths lingered and blended. Haze played a larger role, built from gases and particles released by relentless volcanism and slow chemical reactions. Instead of clarity, the sky often held a muted translucence, filtering sunlight into tones that shifted with atmospheric balance. Color emerged not as brilliance, but as suggestion, shaped by diffusion rather than sharp contrast. Keeping the planet warm under this dimmer star required chemistry to step in where sunlight could not. Greenhouse gases accumulated gradually, thickening the air with heat trapping potential. Carbon dioxide and methane worked quietly, slowing the escape of warmth back into space. The atmosphere became a careful blanket rather than a clear window, allowing liquid water to persist and life to continue its patient experiments. This warming came with visual consequences, altering how light traveled and returned to the surface. As gases increased, the sky absorbed and scattered light in complex layers. Methane haze softened outlines and shifted colors toward unfamiliar ranges. Sunrises and sunsets, when visible through the veil, would have unfolded slowly, stretching color across the sky with muted persistence. The heavens did not blaze, they glowed, shaped more by chemistry than by direct illumination. Earth's appearance became responsive to balance, sensitive to small changes in gas concentrations and temperature. The seas beneath this altered sky responded in kind. Reduced sunlight penetration changed how light entered the water, interacting with minerals and early life forms suspended near the surface. Reflections softened, and color deepened or dulled depending on the sky above. Ocean and atmosphere mirrored each other through light, connected by chemistry rather than brightness. Through this long era, Earth remained stable not through constancy, but through adaptation. A weaker sun did not hinder the planet, it invited complexity. Chemistry learned to compensate, shaping warmth, reshaping light, and quietly rewriting the sky. Under gentler sunlight, Earth became a world defined not by intensity, but by balance, carrying its evolving colors forward in calm persistence. As life continued its quiet work across shallow seas and warm sediments, methane began to accumulate as an unintentional signature of biology. Microbes that drew energy from simple chemical reactions released this gas steadily, exhaling it into the surrounding water and air. What began as a trace presence slowly grew into something planet shaping. Methane gathered patiently, molecule by molecule, until it could no longer remain unseen. In large amounts, methane alters the character of the sky. Sunlight moving through a methane-rich atmosphere meets resistance, not as a hard barrier but as a veil. High in the air, methane reacts under solar energy to form complex organic particles, fine enough to float, yet dense enough to matter. These particles assemble into atmospheric hazes, spreading like smoke that never fully clears. The sky becomes layered, textured, and softly obscured. Light passing through this haze behaves differently. Shorter wavelengths, especially those associated with blue light, scatter and weaken as they move through the suspended particles. Instead of traveling cleanly across the sky, they diffuse, losing intensity before reaching the surface. What remains is a gentler palette, dominated by muted tones that drift toward pale yellows, soft ambers, or dim grays depending on thickness and chemistry. The sky ceases to express clarity and begins to express depth. This haze becomes the planet's first filter, an atmospheric lens shaped by living processes. It does not stop sunlight entirely, but reshapes it, redistributing energy and color as it descends. The effect reaches beyond appearance. By blocking some incoming radiation while trapping warmth below, methane haze contributes to climate stability beneath a fainter sun. Temperature and light become negotiated outcomes rather than fixed conditions. Beneath this filtered sky, the surface adapts. Oceans receive a softened spectrum, changing how light penetrates the water and reflects back upward. The horizon blurs and contrasts flatten. Days unfold under a sky that feels present but distant, luminous but restrained. Color becomes subtle, emerging through layers rather than shining directly. This transformation does not arrive with ceremony. It builds gradually, almost imperceptibly, as methane continues to rise and haze thickens in response. Life and atmosphere engage in a slow exchange, each reshaping the other without awareness or intention. The planet's appearance responds faithfully, recording these shifts in light rather than sound or motion. Through methane haze, Earth learns one of its earliest lessons in appearance. Color is not merely a result of light arriving from the sun, but of everything it passes through on the way. With enough methane in the air, blue skies become optional rather than inevitable, replaced by a quieter world where light arrives already softened, already shaped by life itself. In this earlier chapter of Earth's story, the sky rarely offered clarity. Transparency was not yet a defining feature of the atmosphere because the air itself was restless. Fine particles drifted continuously, suspended for long stretches of time, softening outlines and muting distance. What later ages would recognize as a clear day simply did not exist. The sky was present, luminous and active, but never still. Volcanic activity played a constant role in this restlessness. Across the planet, fissures opened and closed, releasing gases and ash into the air with patient regularity. Eruptions did not arrive as singular catastrophes separated by long, quiet intervals, but as part of Earth's steady breathing. Each release added new material to the atmosphere, refreshing its haze and reinforcing its opacity. Ash settled slowly, sulfur rose and lingered, and the sky absorbed it all. Sulfur compounds became especially influential. Lofted high into the air, they transformed into aerosols that reflected and scattered incoming sunlight. These particles did not fall quickly. They hovered, spreading thin veils across entire regions, sometimes across the globe. Light passing through them lost its sharpness, filtered into gentler tones before reaching the ground. The sky became less a window and more a glowing surface, shaped by what it carried rather than what lay beyond it. This persistent haze reshaped how Earth appeared from every angle. Horizons blurred, distances softened, and shadows faded. Colors merged rather than separated, creating a world defined by gradation instead of contrast. Even when sunlight was strong, its arrival was tempered by the material suspended in the air. Days unfolded beneath a luminous ceiling that felt close, as if the sky itself were part of the surface world. Such conditions made stability rare. The atmosphere was always responding, adjusting to new inputs of gas and dust, rarely settling into equilibrium. A clear blue sky, as it exists now, requires consistency. It depends on long periods without major disruption, on predictable chemistry, and on an atmosphere allowed to rest. Early Earth offered none of these conditions. Change arrived too frequently, chemistry shifted too often, and the air remained in motion. Under these skies, the planet's appearance reflected its internal energy. Earth was still releasing heat, still shaping itself, still learning how to breathe. The sky recorded this process faithfully, layer by layer, never hiding the turbulence beneath. Clarity would come later, after balance emerged and the atmosphere learned restraint. For now, the sky remained full, textured, and alive with particles, carrying the quiet evidence of a world still settling into itself. As haze thickens and settles into the atmosphere, sunlight no longer arrives unchanged. Before it ever reaches the ground, it passes through layers of suspended particles, each interaction softening and reshaping what remains. Light that once traveled cleanly now diffuses, scattering gently as it moves downward. The journey becomes longer, quieter, and less precise, and color responds with the same patience. Blue light fades first. Its shorter wavelengths scatter easily, colliding with particles and losing coherence as they drift. Instead of concentrating overhead, blue disperses across the sky and weakens, its presence diluted until it becomes difficult to distinguish. What replaces it is not darkness, but a gradual surrender of sharpness. The sky does not change suddenly, it simply leans away from blue. Longer wavelengths endure this passage more successfully. Yellows, ambers, and soft reds carry farther through haze, bending rather than vanishing, slipping between particles with less resistance. As these tones accumulate, the sky adopts a warmer cast. It glows rather than shines, offering color that feels diffused and spread thin across space. The shift is continuous, unfolding over countless days as haze remains suspended above the surface. This filtered light reshapes everything beneath it. Landscapes soften, and the boundary between air and ground blurs. Shadows lose contrast, becoming shallow impressions rather than sharp outlines. Water reflects the sky's altered tone, carrying warmth into its surface even as depths remain dark. Color does not disappear, it reorganizes, guided by what survives the descent through the air. In such a world, greenish hues can emerge without spectacle. When yellow light blends with faint blue remnants, the result is subtle, neither vivid nor strange. It lingers quietly, tinting the sky just enough to feel different without demanding attention. These colors do not announce themselves. They persist gently, day after day, shaped by steady atmospheric conditions rather than momentary events. Nothing about this process feels dramatic from the surface. There are no sudden changes to mark its arrival, no moments of realization. The sky remains familiar in structure while unfamiliar in tone, offering continuity rather than disruption. Life beneath it adapts without urgency, continuing its cycles under light that has simply grown softer and warmer. In a hazy world, color becomes an atmosphere rather than a feature. It is something inhabited rather than observed, present in every direction at once. The sky settles into its filtered palette with calm persistence, holding its hues quietly, shaped by particles drifting high above. Over time, this subtlety becomes normal, and the planet wears its shifted colors as easily as it once wore blue. The ocean's familiar blue often feels as natural as water itself, yet this color is not an inherent trait of the sea. Pure water, when isolated from sky and life, behaves differently with light. As sunlight enters the surface, warmer wavelengths are absorbed first. Reds fade quickly, followed by oranges and yellows, leaving behind shorter wavelengths that travel farther. This quiet filtering happens within the water alone, long before reflection or biology adds its influence. Yet, absorption is only part of the story. Blue does not emerge automatically from this process. It requires clarity, depth, and an open path for light to move downward and return upward. In clear water, remaining blue wavelengths scatter back toward the surface, creating the familiar appearance. When clarity is lost, this pathway breaks. Suspended particles interrupt the journey, absorbing or redirecting light before it can return. The sea then shifts in tone, becoming green, brown, or gray depending on what fills it. Life plays an equally powerful role at the surface. The upper layers of the ocean are not empty, but crowded with microscopic organisms drifting in light-rich waters. These organisms absorb specific wavelengths for energy, especially reds and blues, altering how light behaves in the water column. Their pigments reshape the balance of reflected color, often pushing the sea toward green hues where life is dense. The ocean's appearance becomes a living signal, shaped by biology as much as physics. When surface life changes, color responds without delay. Blooms of microorganisms tint vast regions, visible even from great distances. Declines restore clarity, allowing blue to re-emerge. The ocean's color is therefore not fixed, but conditional. It reflects who is present near the surface and how they interact with light. Chemistry, clarity, and life move together, each influencing what the eye perceives. Under skies already softened by haze and altered light, these effects become more pronounced. Reduced blue light from above means less blue available to scatter below. Warm tones dominate the incoming spectrum, and surface life adjusts accordingly. The sea responds by reflecting what it receives, carrying the sky's filtered character downward. Water becomes a canvas that mirrors atmospheric change. In this way, the ocean reveals its dependence. Blue is not its default state, but a momentary alignment of clear skies, balanced life, and unobstructed light. Remove or adjust any one of these conditions, and the sea quietly transforms. Its color shifts without announcement, guided by processes unfolding just beneath the surface. The ocean has never promised constancy. Across Earth's long history, it has worn many colors, each shaped by the conditions above and the life within. Blue is only one chapter in that story, resting gently between others, waiting to change again when the planet's balance moves on. Long before green became the dominant color of life on land and sea, the planet was shaped by organisms that solved survival through different solutions. Green plants, so familiar in the modern world, arrived late in Earth's story. For vast stretches of time, life persisted without leaves, forests, or fields. The surface was guided instead by simpler forms, spread thinly across water and stone, quietly absorbing light in ways that now feel unfamiliar. These early organisms faced a difficult problem. Sunlight reached the planet already altered by haze, chemistry, and distance. The spectrum available at the surface was uneven, filtered, and often subdued. Rather than reflecting green, many early life forms relied on pigments tuned to longer wavelengths. Purples, reds, and browns dominated microbial mats and shallow waters, absorbing light that penetrated the atmosphere more reliably. These pigments gathered energy patiently, matched to the world they inhabited. Each pigment acted as a quiet agreement with sunlight. Some absorbed green and reflected red or violet. Others captured wavelengths that slipped past competing organisms. The surface became a patchwork of tones, not sharply divided but gently blending where communities met. Color did not serve appearance, it served survival. What remained visible to the eye was only a byproduct of what life consumed. Without widespread green life, the land remained mostly bare. Microbial films clung to damp rock and sediment, darkening shorelines and shallow basins. These layers altered how light interacted with the ground, absorbing warmth and reducing reflection. From above, the planet would have appeared darker, more muted, shaped by pigments that swallowed light rather than scattering it back. The brightness associated with modern landscapes had not yet emerged. The oceans echoed this pattern. Near the surface, pigments within microscopic life reshaped the water's color, pulling available energy inward. Without green phytoplankton dominating the seas, different hues guided the reflection. Purplish and brown tones softened the surface, blending with the filtered light from above. The ocean's appearance reflected its inhabitants, just as it always would, but the inhabitants told a different story. Over time, this world settled into its rhythm. Pigments, atmosphere, and light formed a stable relationship, balanced but limited. Energy flowed steadily, yet certain wavelengths remained underused. The green portion of the spectrum lingered, passing through many organisms untouched. It existed as an opportunity not yet recognized. In this age, before green life, Earth carried a quieter palette. Colors were present, but subdued, absorbed rather than displayed. The surface held its energy close, shaped by pigments adapted to scarcity and shade. The planet waited patiently, unaware that a new solution to light would eventually transform its appearance, turning unused wavelengths into the foundation of a greener world. Before green life reshaped the planet's surface, other solutions quietly dominated. Among the earliest and most widespread were microbes whose pigments followed a different logic, tuned not to reflect green, but to consume it. These organisms lived beneath hazy skies and filtered sunlight, adapting to an environment where certain wavelengths traveled more reliably than others. Their strategy was simple and effective, shaped by the light that reached them each day. These microbes relied on pigments unlike chlorophyll. Instead of absorbing red and blue light, they captured green wavelengths, drawing energy from the middle of the spectrum. What they did not absorb was reflected outward, returning purples, reds, and deep browns to the surface world. Color became an accidental signal, a quiet consequence of survival rather than a display. The land and sea did not glow vividly, but they carried subtle tints that shifted with light and life. In shallow waters, these organisms formed dense layers. Sunlight filtered through atmosphere and water, arriving already softened. Green wavelengths slipped through competing absorbers and reached these microbial communities efficiently. The pigments waiting there captured that energy, fueling metabolism and growth. What remained drifted back toward the surface as muted purple tones, blending with the haze above and the minerals below. On damp shorelines and exposed sediments, similar communities spread thinly across rock and soil. Their colors deepened when wet, darkened under shadow, and softened in direct light. From a distance, the surface appeared bruised rather than bright, marked by subtle color fields instead of sharp contrasts. These ecosystems did not dominate through height or complexity, but through patience and persistence. For long stretches of time, this approach shaped entire ecosystems. Purple pigmented microbes formed the foundation of food webs, supporting layers of life adapted to their chemical outputs. Energy flowed steadily through these systems, balanced with the filtered light of the age. Nothing demanded change. The pigments worked well within the constraints of the world they inhabited. The presence of these organisms influenced the planet's appearance in quiet ways. Oceans reflected altered tones where microbial life thickened near the surface. Shallow seas leaned toward dusky colors, absorbing and returning light differently depending on who lived there. Land surfaces followed similar patterns, responding to moisture, chemistry, and the spread of microbial films. This era did not feel transitional from within. Life had solved its light problem in a way that fit the planet's conditions. Green light was abundant, usable, and reliable, and these microbes made full use of it. Their purple reflections lingered across Earth's surface, steady and unassuming, marking a chapter where life and light moved together in balance, long before green would claim the stage. In this period of Earth's history, oceans did not yet carry the depth and darkness associated with the modern world. Vast regions were shallow, spread thinly across continental shelves warmed by persistent geothermal heat and filtered sunlight. Water moved slowly across these basins, lingering long enough for life to settle and shape the surface beneath. The sea was not an empty volume, but a living layer stretched across stone. Microbial mats thrived in these conditions. They spread outward in wide carpets, layered and resilient, binding sediment beneath them and transforming the seabed into an active interface between water and life. These mats were not hidden in the depths. They occupied the very surface of the ocean floor, often reaching upward toward the light itself. Their presence turned large portions of the sea into a biological skin. When sunlight entered these shallow waters, it did not travel far before meeting life. Instead of scattering through empty space, light encountered pigments almost immediately. Energy was absorbed, transformed, or reflected back upward directly from living surfaces. The ocean's appearance became tightly coupled to the organisms growing within it. Color emerged not from depth or reflection of the sky, but from biology holding the light at the boundary. This interaction gave the sea a distinct character. Where microbial mats were dense, the surface reflected darker, richer tones shaped by the pigments in use. Purples, browns, and muted reds softened the water's face, blending gently with the filtered light from above. The sea did not shimmer with clarity. It absorbed presence, appearing solid and grounded rather than transparent. Because these seas were shallow, depth played a limited role in appearance. Light rarely penetrated far enough to scatter and return from within the water itself. Instead, what the eye perceived came from the living layer beneath the surface. The sea acted as a mirror not of the sky, but of its inhabitants. Changes in microbial composition subtly altered the color and texture of entire regions. This biological dominance created a calm visual consistency. The water's appearance remained stable so long as the microbial communities remained intact. Movement came slowly, shaped by growth and decline rather than waves or currents. From a distance, coastlines and shallow basins blended into continuous fields of color, their boundaries defined by life rather than land. In such a world, the ocean told a quiet truth about the planet. Appearance followed metabolism. What lived at the surface determined what the sea revealed to the light above. These shallow seas recorded biology directly, reflecting it back into the atmosphere with patient clarity. Earth's early oceans were not blue expanses hiding unknown depths. They were living surfaces, intimate and expressive, carrying the colors of their inhabitants without disguise. In their stillness and warmth, the seas became faithful mirrors of life itself, holding its presence gently at the edge between water and sky. A purple sea is not the result of pigment dissolved into water, nor the product of imagination layered onto the past. It emerges from something far quieter and more grounded. Color appears when life gathers densely enough to shape how light returns to the sky. In these ancient oceans, purple was not painted across the surface. It rose from it, assembled from countless living bodies working in unison. These seas were capped by thick biological layers. Microbial communities formed continuous mats across shallow basins, pressing close to the interface between water and air. Each cell carried pigments tuned to the available light, absorbing what sustained it and reflecting what remained. Alone, each organism altered almost nothing. Together, they transformed entire regions. Their combined effect created surfaces that behaved differently from open water, responding to sunlight as living terrain. Light striking these dense layers did not penetrate far. It met resistance almost immediately, scattered and redirected by pigments arranged in overlapping sheets. Green wavelengths were drawn inward, used efficiently and consistently, What escaped was shaped by that collective appetite. Purples and muted reds returned upward, softened by haze and distance, yet unmistakable in tone. The sea became visible, not through depth, but through presence. This color did not fluctuate with passing clouds or shifting angles of the sun. It persisted because the biology beneath remained stable. The hue belonged to the ecosystem, not the moment. As long as the mats thrived, the surface held its color. Change occurred slowly, guided by growth, competition, and chemical balance rather than weather or tide. From above, the ocean would have appeared textured rather than transparent. Its surface signaled where life concentrated, tracing coastlines and shallow shelves with subtle distinction. Purple was not a highlight, it was a summary. It represented metabolism spread across kilometers, energy captured and reused endlessly at the boundary between light and water. This visibility marked an important threshold. Life was no longer hidden entirely beneath the surface or locked within isolated niches. It had become extensive enough to imprint itself onto the planet's appearance. The sea reflected not just the sky above, but the collective activity below, turning biology into a visible planetary feature. Understanding this shifts how the scene is read. A purple sea does not indicate rarity or extremity, it indicates success. It reveals ecosystems that reach sufficient scale to influence the flow of light itself. The color is calm, earned through persistence rather than spectacle. In this context, purple becomes a surface language. It speaks of coordination, of countless lives aligned by shared chemistry and steady conditions. The sea wears this color naturally, not as decoration, but as evidence that life has settled in deeply enough to be seen from above, quietly and clearly. The accumulation of oxygen did not arrive as an announcement. It began quietly, released in small amounts by life that had learned to draw energy from sunlight in a new way. For a long time, this oxygen vanished almost as soon as it appeared, consumed by metals, rocks, and dissolved compounds waiting to react. The atmosphere absorbed it hungrily, allowing none to linger. Earth remained outwardly familiar, even as its internal balance began to shift. As oxygen continued to seep into the air and water, chemistry responded with force. Oxygen is restless, eager to bond, and the early planet offered endless opportunities. Iron dissolved in the oceans, transformed and settled to the seafloor. Gases that once defined the atmosphere broke apart or faded away. Methane thinned, sulfur compounds retreated. Reactions cascaded quietly across the globe, rewriting the chemistry of sky and sea without pause. These reactions altered how light moved through the atmosphere. The hazes that once softened the sky began to thin as oxygen disrupted their formation. Particles that had lingered for ages lost their support and fell away. The canopy above the planet brightened, not suddenly, but steadily, as clarity increased and familiar scattering returned. The sky changed its tone again, shaped now by a different balance of gases and light. For many forms of early life, this shift was catastrophic. Oxygen, so useful to later organisms, acted as a toxin to those shaped by its absence. Cells adapted to ancient chemistry struggled as their internal processes failed under oxidative stress. Entire ecosystems thinned and vanished, leaving behind chemical traces rather than living communities. The surface world grew quieter in places where life had once flourished openly. Yet this loss unfolded slowly. There were no sharp boundaries between before and after, only a long transition marked by decline and adaptation. Some organisms retreated to sheltered niches, where oxygen remained scarce. Others evolved defenses, slowly adjusting their internal chemistry to survive the new conditions. Life did not resist change, it absorbed it, reshaping itself in response. As the atmosphere continued to transform, Earth crossed a threshold it would never return from. Oxygen stopped being a fleeting presence and became a defining feature. The planet's appearance followed suit. With changing chemistry came new interactions with sunlight, setting the stage for clearer skies and different colors to emerge over time. This first atmospheric turning point marked a quiet division in Earth's story. It separated a world ruled by ancient chemistry from one preparing for complexity. The sky did not merely change color, it changed allegiance, aligning itself with a new form of life and a new direction. The planet moved forward gently, carrying loss and possibility together into the ages that followed. When oxygen crossed from rarity into persistence, its presence reshaped life with quiet finality. For organisms built in its absence, oxygen was not a gift but a danger. It disrupted internal chemistry, damaged delicate molecular systems, and interfered with energy pathways refined over immense spans of time. Life that had flourished comfortably beneath hazy skies and shallow seas now faced conditions it had never needed to resist. This shift unfolded gradually, yet its consequences were sweeping. Ecosystems that depended on oxygen-free environments began to thin. Microbial communities that once spread confidently across sediments and waters retreated or disappeared. Their collapse did not announce itself with noise or upheaval. It happened cell by cell, layer by layer, as habitats lost the chemical stability they required. The surface world grew quieter as familiar biological signatures faded. Pigments that had once shaped the planet's appearance vanished alongside the organisms that carried them. The purples and dark reds, reflected by dense microbial mats, became rarer in open waters. As oxygen altered the chemistry of both air and sea, the light environment shifted again. Surfaces, once dominated by absorptive life, began to clear, allowing different interactions between sunlight and water. The ocean's face softened, losing the biological imprint that had defined it for so long. Some life endured by withdrawing. Sheltered environments, buried sediments, and deeper waters offered refuge where oxygen struggled to penetrate. In these spaces, ancient metabolisms persisted, continuing their cycles unseen. The open surface, however, belonged increasingly to organisms willing to tolerate or exploit the new chemistry. Change did not require intention, it required only survival under new rules. As older ecosystems receded, others expanded quietly into the available space. Oxygen reshaped the boundaries of habitability, opening paths for new metabolic strategies. Energy could now be extracted more efficiently, supporting greater complexity over time. The transformation did not rush. It progressed with the same patience that had always guided the planet, allowing replacement rather than abrupt erasure. Earth did not mourn what it lost. It recorded change in chemistry, in light, and in color. The sky responded to the thinning of haze. The seas reflected different tones as biological surfaces withdrew. The planet's appearance shifted not because it sought a new form, but because it followed the consequences of its own evolving atmosphere. In this transition, one world quietly gave way to another. Ancient life retreated into shadow, while new life prepared to occupy the light. The process left no boundary line to mark its passage. It flowed onward, steady and inevitable, carrying Earth forward as it always had, reshaping the surface gently as chemistry and life learned to coexist in a newly oxygenated world. As Earth continued to change, a different approach to light slowly proved more resilient. Organisms using chlorophyll gained access to a wider portion of the solar spectrum, gathering energy from wavelengths that had once passed through earlier life unused. This broader reach did not offer instant dominance, but it allowed steady growth under increasingly varied conditions. Light that had once been surplus became fuel, and that advantage accumulated patiently over time. Chlorophyll worked especially well beneath a brightening sky. As oxygen altered atmospheric chemistry, haze thinned and clarity increased. More light reached the surface, arriving with a stronger presence of blue and red wavelengths. Organisms capable of capturing this expanded range found themselves better matched to the new world forming above and below. Their metabolism aligned naturally with the planet's shifting balance. At the same time, oxygen producing life reshaped the atmosphere in its own image. As photosynthetic organisms spread, they released more oxygen, reinforcing the conditions that favored them. Each increase in oxygen reduced the dominance of ancient gases, further clearing the sky and stabilizing the climate. The atmosphere became less variable, less reactive, and more predictable. Light followed suit, arriving with greater consistency from day to day. These changes created feedback loops that quietly locked themselves in place. Clearer skies favored chlorophyll-based life. That life increased oxygen. Oxygen maintained clarity and stability. Each step supported the next, forming a self-reinforcing pattern that grew stronger with time. Purple pigmented organisms did not fail through weakness, but through mismatch. The environment they once mastered no longer existed at the surface. As conditions shifted, purple ecosystems retreated to environments where their advantages still mattered. Sheltered waters, sediments, and isolated niches preserved traces of the older world. Meanwhile, green life expanded across oceans and eventually onto land, painting the surface with a new dominant hue. The planet's appearance followed this biological rearrangement faithfully. Green became stable not because it was inevitable, but because it fit the new equilibrium. The interaction between atmosphere, light, and life settled into a balance that favored reflection of green wavelengths. Forests, fields, and plankton-rich seas emerged slowly, each reinforcing the planet's modern colors. What once lingered as unused light now defined the surface. Through this long transition, Earth replaced one visual language with another. Purple did not vanish abruptly. It withdrew gracefully, yielding ground to a system better suited to the planet it had helped create. The world did not choose green. It arrived there through chemistry, light, and life moving together, step by patient step, until the colors we recognize today became simply the most stable expression of a living planet. As microbial mats retreated from the open seas, the ocean's surface began to change in character. The dense living layers that once intercepted light so immediately grew thinner, breaking apart as oxygen altered shallow environments. Without these continuous biological skins, light gained the freedom to travel deeper into the water column. The sea slowly shifted from a living surface into a volume, layered and open, allowing new interactions between light and depth. In their place, plankton rose quietly into prominence. These microscopic organisms did not cling to sediments or form carpets. They drifted, suspended within the upper layers of the ocean, moving with currents and light alike. Their presence was diffuse rather than fixed, spread thinly across vast areas. This distribution changed how the ocean handled incoming sunlight. Light no longer struck a single surface of life, but passed through countless drifting cells before continuing downward. Plankton reshaped the sea's reflectivity in subtle ways. Their pigments absorbed selected wavelengths while allowing others to pass, but they never formed a solid barrier. Instead, They filtered light gradually, softening it as it descended. What remained scattered back upward from greater depths, returning with a cooler tone. The ocean began to reflect not the color of its inhabitants directly, but the physics of water itself. As oxygen stabilized atmospheric chemistry, water clarity increased alongside it. Reduced haze above meant more consistent light entering the sea, and fewer suspended particles within the water allowed deeper penetration. Red and yellow wavelengths continued to fade quickly, absorbed within the upper layers. Blue traveled farther, scattering repeatedly until it returned to the surface. This process unfolded patiently, relying on clarity, depth, and time rather than sudden change. Blue did not assert itself immediately. For long ages, the ocean held mixed tones shaped by biology, chemistry, and light together. Only as microbial dominance waned and plankton-based systems settled into balance did blue begin to emerge as a persistent feature. The sea learned to reveal its depth, allowing light to return shaped by distance rather than proximity to life. This transition marked a quiet milestone in Earth's visual history. The ocean became less expressive of surface biology and more reflective of planetary scale processes. Its color now spoke of clarity, of deep water, of stable skies above, and oxygen-rich air beyond. Blue came not from decoration, but from openness. By the time blue oceans became familiar, Earth had already passed through many worlds. Purple surfaces, hazy skies, and biologically saturated shallows had shaped earlier chapters. Blue arrived late, settling in only when conditions allowed it to endure. It became dominant not through inevitability, but through balance. The ocean finally reflected depth itself, carrying the calm signature of a planet that had learned, slowly, how to hold light across its vast interior. As oxygen continued to accumulate, a quiet transformation unfolded high above the surface. Some of this oxygen drifted upward, where intense sunlight reshaped it into a new form. Ozone gathered slowly in the upper atmosphere, thin at first, then gradually thickening into a persistent layer. This development did not draw attention from below, yet it changed the relationship between Earth and the Sun in a lasting way. With ozone present, ultraviolet light no longer reached the surface unfiltered. Energetic radiation that had once interacted directly with air, water, and living tissue was absorbed high above, warming the upper atmosphere instead of disrupting the world below. This filtering softened the chemistry of the sky. Fewer reactions were triggered by incoming light, and fewer transient particles formed. The atmosphere began to behave with restraint rather than volatility. As ultraviolet intensity diminished, atmospheric chemistry found balance. Reactive gases became rarer, and long-lived components began to dominate. The constant creation and destruction of hazes slowed. Particles that once lingered for ages became less common, allowing the air to remain clearer for longer periods. Day after day, the sky maintained its structure instead of reinventing itself. This stability reshaped how light scattered through the atmosphere. With fewer interruptions, shorter wavelengths dispersed efficiently, filling the sky evenly. Blue light, once weakened by haze and chemical chaos, now traveled freely, spreading across the heavens with consistency. The sky did not need special conditions to appear blue. It arrived there naturally, supported by a settled balance of gases and light. For the first time, color could be trusted. Skies no longer shifted unpredictably from one era to the next or from one region to another. The atmosphere held its form through seasons and centuries, offering continuity rather than surprise. Sunrises and sunsets still carried warmth and variation, but the space between them grew familiar. Blue became the background of the planet's days. Life responded quietly to this reliability. With harmful radiation filtered away, surface environments grew less hostile. Organisms could expand into open air and shallow waters without constant chemical stress. The sky no longer dictated rapid adaptation. It allowed life to settle, to explore new structures, and to build complexity over time. This moment marked more than a visual change. It represented Earth learning how to maintain itself. The formation of ozone connected the atmosphere into a system capable of self-regulation. Oxygen supported ozone. Ozone protected oxygen-producing life, and that life continued to reinforce atmospheric balance. The planet entered a phase where feedback produced stability rather than upheaval. When blue skies became reliable, Earth crossed into familiarity. The heavens stopped reinventing themselves and instead held steady, offering the same hue day after day. This constancy did not erase the planet's long history of change, but it rested upon it. The sky finally locked into place, carrying forward a color that felt timeless only because it had learned, slowly, how to endure. Color leaves no bones behind. It fades long before stone has time to remember. Pigments are fragile things, built for function rather than permanence, and when life ends, their structures collapse quickly. Light stops interacting with them, chemistry breaks them apart, and time finishes the work. What remains is form without hue, texture without tone. The fossil record preserves shape, not surface. Because of this, ancient worlds arrive to the present, muted and incomplete. Seas once tinted by living films leave only layered rock. Skies that filtered light into unfamiliar colors leave no direct imprint at all. Even organisms whose pigments once defined entire ecosystems are reduced to outlines, compressed into stone that carries no hint of how they once reflected the sun. Color slips away silently, leaving scientists to search for subtler signals. Reconstruction begins not with sight, but with chemistry. Pigments vanish, yet the conditions that favored them do not disappear entirely. Minerals record oxidation states. Sediments preserve ratios of elements that reveal whether oxygen was scarce or abundant. Certain molecules, resistant enough to survive deep time, linger as altered fragments known as biomarkers. They do not show color, but they speak of metabolism, of energy pathways, of how life interacted with light. From these traces, scientists infer behavior rather than appearance directly. If oxygen was absent, certain pigments become likely. If methane was abundant, haze becomes part of the picture. If iron shifted from dissolved to solid forms, the atmosphere must have changed. Each clue narrows possibility, guiding reconstruction toward what could exist under those conditions. Color emerges as a consequence, not a guess. Modern analogs help bridge the gap. Living microbes in oxygen, poor waters, salt flats, and volcanic environments demonstrate how pigments respond to specific chemistry and light. These communities offer windows into processes that once shaped the planet broadly. By comparing ancient chemical signatures with living systems, researchers build models of appearance grounded in physics and biology rather than imagination. This process resembles listening rather than looking. The planet does not show its past directly. It hints. Layers accumulate quietly, each holding a fragment of context. With enough fragments aligned, a coherent picture forms. Purple seas are inferred not from preserved color, but from the dominance of pigments that would absorb green light. Hazy skies are reconstructed from the absence of ozone and the presence of reactive gases. Nothing is claimed lightly, and nothing is fully visible. Lost worlds are rebuilt through patience. Each insight arrives from the convergence of many lines of evidence, none sufficient alone. Together they restore motion, chemistry, and light to landscapes long gone. Color returns not as certainty, but as the most stable outcome of known conditions. In this way, the absence of color becomes part of the story. It reminds that Earth's past was not preserved for display. It must be understood through traces, through quiet signals that survive where brilliance does not. The planet speaks softly across time, and science listens carefully enough to hear the shades that once filled the sky and sea. In the modern world, color appears settled and predictable, yet a few quiet places still refuse to follow familiar rules. Scattered across the planet are lakes, lagoons, and shallow basins where water turns red, pink, or purple under certain conditions. These colors are not stains or reflections. They rise from life, responding to chemistry that echoes an earlier Earth. In these environments, extreme conditions shape survival. Salinity climbs beyond what most organisms can tolerate. Oxygen dwindles or vanishes. Sunlight arrives unfiltered by depth, striking shallow waters directly. In this narrow balance, ancient strategies reappear. Microbes equipped with alternative pigments thrive where green life falters. They absorb light differently, reflecting colors that feel unexpected only because they are rare today. Salt lakes offer some of the clearest examples. As water evaporates, minerals concentrate and oxygen levels drop. Microbial communities adjust, producing pigments suited to intense light and chemical stress. Reds and purples spread across the surface, shifting with season and salinity. The water becomes a living signal, its color announcing which metabolisms are active below. Similar transformations occur in certain tropical lagoons and volcanic waters. There, sulfur-rich chemistry and limited circulation create stable niches for organisms that resemble Earth's early inhabitants. Their pigments intercept wavelengths that modern ecosystems largely ignore. The result is color shaped by necessity rather than novelty, persistent so long as conditions hold. These places do not recreate the past fully, but they preserve pieces of it. They demonstrate how life behaves when oxygen is scarce, when chemistry dominates, and when light arrives without moderation. In doing so, they lend weight to reconstructions of early Earth. Models predicting purple seas and tinted skies are no longer abstractions when their logic plays out in living systems today. Scientists study these environments carefully, tracing chemical gradients and microbial layers. The data they gather aligns with ancient records preserved in stone. Element ratios, mineral deposits, and biological behavior converge. The same rules apply across time. Given similar conditions, life returns to familiar solutions. What makes these sites remarkable is not their rarity, but their persistence. They endure quietly, often overlooked, tucked into harsh landscapes where few linger. Yet they carry deep history within their shallow waters. Each bloom and fade mirrors processes that once shaped the planet on a grand scale. These modern anomalies remind that Earth has not erased its earlier selves completely. It has folded them inward, preserving them where conditions allow. In red lakes and purple lagoons, the planet rehearses its memory, revealing how color once emerged naturally from chemistry and life acting together. They stand as living echoes, not frozen relics. Their colors shift, breathe, and respond, just as ancient oceans once did. Through them, the past remains active, quietly confirming that Earth's earlier palettes were not imagined but lived. Rebuilding an ancient sky begins without color. It starts with physics, with light treated as motion rather than appearance. Scientists model how sunlight scatters through gases of different compositions, densities, and temperatures. By adjusting these variables, they observe how wavelengths would behave under unfamiliar conditions. Blue fades or strengthens, warmth spreads or withdraws, and the sky's tone emerges as a mathematical outcome rather than an artistic choice. These light scattering models form a foundation, but they do not stand alone. They are layered with atmospheric simulations that recreate early Earth chemistry in motion. Computers track how gases interact, how haze forms or collapses, and how ultraviolet radiation reshapes the upper atmosphere. These simulations run across immense spans of time, allowing patterns to stabilize. When conditions settle into balance, the resulting sky reveals its character, shaped by chemistry rather than assumption. Biology adds another essential dimension. Pigments used by living organisms leave chemical descendants even after their color disappears. Fragments of molecular structures persist as altered compounds preserved in sedimentary rock. By identifying these remnants, scientists infer which pigments once dominated the surface. Each pigment corresponds to specific light absorption behaviors. From that, reflected colors can be predicted with reasonable precision. Laboratory studies extend this process. Modern microbes grown under controlled conditions demonstrate how pigments respond to different atmospheres and light environments. When these results match chemical signatures found in ancient rocks, confidence grows. The same physical rules apply, regardless of era. Life reacts predictably to light and chemistry when placed under comparable constraints. Geological evidence weaves through every step. Mineral layers record oxidation events, volcanic inputs, and atmospheric shifts. Iron formations mark the rise of oxygen. Sulfur isotopes trace changes in ultraviolet exposure. Each record narrows the range of possible skies. When independent clues converge, improbable scenarios fall away, leaving a small set of conditions that fit all observations. What makes these reconstructions reliable is not any single method, but their overlap. Light models align with chemical simulations. Biological evidence supports geological records. Modern analog environments behave according to the same principles predicted by theory. Each line of evidence corrects the others, preventing imagination from drifting too far from reality. The result is not a photograph, but something steadier. It is a constrained vision built from agreement rather than speculation. Ancient skies emerge as products of measurable forces acting together, not as aesthetic choices assigned after the fact. Through this careful assembly, scientists rebuild worlds that no eye ever witnessed. Color returns as consequence, not guesswork. The sky's past becomes legible through patience, mathematics, chemistry, and living examples. In listening to these overlapping signals, Earth's lost atmospheres reveal themselves quietly, shaped by rules that continue to govern the light above us today. Earth has never worn a single face. What appears stable from within one lifetime dissolves when stretched across deep time. The planet has passed through distinct appearances, each shaped by chemistry, light, and life moving together. These were not brief anomalies or experiments. They were complete worlds, coherent and self-reinforcing, each as real and persistent as the one experienced today. During every phase, the planet settled into balance. Skies took on particular tones, oceans reflected specific colors, and surfaces held consistent textures. These conditions did not flicker or alternate rapidly. They endured for immense spans, long enough for ecosystems to adapt fully and for landscapes to feel finished. Within each phase, the planet appeared resolved, as if it had arrived at its final form. Life responded by treating those conditions as permanent. Organisms evolved to match the light available, the gases present, and the chemistry of water and air. Pigments aligned with spectra, metabolisms aligned with atmospheric limits. Entire ecosystems formed under assumptions that held true for millions of years. Nothing about those worlds suggested transition while they existed, yet each phase carried the quiet seeds of change. Life altered the air, chemistry reshaped light, geological processes shifted circulation and balance. None of this felt dramatic from the surface. Change accumulated slowly, unfolding beneath the appearance of constancy. One stable world gave way to another not through collapse, but through replacement. The purple seas and tinted skies of earlier ages were not incomplete versions of today. They were complete expressions of Earth under different conditions. In the same way, hazy atmospheres, dimmer suns, and biologically saturated surfaces formed worlds that functioned smoothly within their own rules. They were not steps toward a goal. They were destinations reached and inhabited fully. The modern world follows this same pattern. Blue skies, blue oceans, and green continents feel permanent because they have remained consistent within recorded history. Life has adapted to them so completely that they seem inevitable. Yet these features rest on balances that emerged only after many other arrangements passed away. They are stable now, but they are not guaranteed forever. Understanding Earth as a series of worlds softens the illusion of finality. The planet does not evolve toward a single preferred appearance. It explores what is possible within physical limits, lingering wherever balance can be maintained. Each world holds until chemistry, biology, and energy find a different alignment. Seen this way, the present is not the destination, but the current chapter. It is a world as real and immersive as those before it, shaped by conditions that feel permanent only because they are active now. Earth continues its long habit of becoming something stable, inhabiting it fully, and eventually moving on, carrying forward the quiet truth that appearance is always temporary, even when it feels complete. This history carries a quiet unease, not because it is violent, but because it is unfamiliar in scale. Human memory is brief, shaped by lifetimes that flicker and fade quickly. Within that narrow window, the world appears consistent. Skies remain blue, seas stay blue, seasons repeat themselves with reassuring order. What repeats feels permanent, and permanence feels safe. Familiarity settles deeply. It teaches the mind to treat what is constant as natural and what is rare as impossible. Landscapes that persist across generations begin to feel anchored beyond time. The idea that oceans could once appear purple or skies could carry unfamiliar hues does not immediately threaten logic. It unsettles comfort. It suggests that what feels fixed may simply be momentary alignment. Deep time presses gently against that instinct. It stretches perspective beyond stories passed down or records preserved. In that expanse, stability becomes temporary by definition. Conditions hold only as long as chemistry, biology, and energy allow them to. When that balance shifts, the world follows without pause or intention. Nothing malicious drives the change. It unfolds because physical rules continue operating. This realization feels destabilizing because it removes the sense of arrival. The modern world stops feeling like the destination of history and instead becomes a passing state. Blue skies are no longer the reward at the end of planetary struggle. They are the result of processes that could shift again under different conditions. The comfort of inevitability dissolves. The planet offers no promise of constancy. It does not preserve appearances for attachment or expectation. Earth responds to feedback, not sentiment. When life altered the atmosphere, the sky changed. When chemistry reshaped light, the oceans followed. These adjustments did not consult future observers. They simply occurred, guided by balance and consequence. What unsettles is not the idea of change, but the absence of preference. Earth does not favor the present arrangement because it benefits humans. It tolerates it because it works within current constraints. That tolerance feels stable only because those constraints remain aligned. Should they drift, the surface will respond as it always has. Yet there is quiet reassurance within this discomfort. The same rules that allowed past worlds to persist also allow the present one to exist. Stability arises when conditions support it, and for now they do. The planet has held this form long enough for life to grow complex, reflective, and aware of its own history. Understanding this history does not demand fear or detachment. It asks for humility. It reframes comfort, not as a guarantee, but as a temporary gift. Earth has carried many worlds before this one, each feeling complete in its time. The present world joins that lineage, neither fragile nor eternal, simply current. When scientists look outward, color becomes more than appearance, it becomes a clue. Planets reflect light according to what covers their surfaces and fills their skies. On Earth, blue oceans and green continents announce biology clearly, but this clarity is a recent development. The planet's earlier chapters reveal that life does not require familiar colors to leave its mark. Color can signal biology even when it appears strange. Pigments evolve to match available light and chemistry, not to satisfy expectation. On worlds where atmospheres filter sunlight differently, or where surface chemistry favors alternate metabolisms, life may announce itself through purples, reds, browns, or muted tones unfamiliar to modern eyes. These colors are not cosmetic. They are functional outcomes of survival. For this reason, a purple or red planet does not imply lifelessness. It may indicate biology operating under conditions unlike those on Earth today. Ancient ecosystems on this planet once produced surfaces that would appear alien if seen without context. Yet those worlds functioned smoothly, supporting robust cycles of energy and matter. Recognizing this widens the lens through which distant planets are interpreted. Earth's past expands the search for life by loosening assumptions. Habitability does not demand blue skies or green vegetation. It does not require oxygen, rich air, or transparent oceans. Life can persist beneath haze, within shallow seas, or under skies tinted by unfamiliar chemistry. What matters is not resemblance, but compatibility between energy sources and living systems. Modern telescopes already glimpse hints of color on distant worlds. As data improves, these hints will grow sharper. Interpreting them demands restraint. A planet lacking Earth's palette should not be dismissed. Instead, its colors should be examined for internal consistency. Do they align with known chemical processes? Do they suggest surfaces actively interacting with light rather than passively reflecting it? This perspective reframes discovery. The goal shifts from finding another Earth to recognizing other Earths, worlds that are complete within their own conditions. Each may carry colors shaped by unique balances, just as this planet once did. Life elsewhere may not look familiar, but familiarity has never been a requirement for persistence. Understanding this also softens the boundary between the known and unknown. Earth's history acts as a translator, showing how radically different appearances can arise from the same physical laws. Purple seas did not violate chemistry. Hazy skies did not prevent ecosystems from thriving. They were outcomes of alignment, not anomalies. In this light, the universe becomes more welcoming. Worlds once dismissed as too strange gain relevance. Color transforms from decoration into evidence. The lesson carried outward is gentle but profound. Life adapts to what exists, not to what is expected. By learning to read unfamiliar colors, the search for life becomes broader, calmer, and more faithful to how planets truly behave across time. Earth often feels complete because it holds still within the span of a human life. Mountains remain, oceans return to their shores, skies repeat their colors with dependable rhythm. This consistency creates the impression of a finished planet, one that has reached its final form. Yet beneath that surface calm, the planet is not resting. It is paused, balanced delicately within conditions that happen to hold for now. Chemistry continues its quiet work everywhere. The atmosphere breathes slowly, exchanging gases between sky, sea, and stone. Oxygen rises and falls within narrow ranges. Carbon moves patiently through living tissue, sediment, and rock. Water circulates endlessly, dissolving minerals, reshaping coastlines, and redistributing heat. None of these processes announce change loudly. They operate continuously, maintaining appearance while preparing the ground for what comes next. This pause is not inactivity, it is equilibrium. Earth settles temporarily, where opposing forces counterbalance each other closely enough to appear stable. Life reinforces that balance by recycling elements efficiently, smoothing extremes, and occupying available niches. The surface looks resolved because feedback loops are holding, not because they have concluded. Stability exists only while those loops remain aligned. History shows how fragile that alignment can be over deep time. Slight shifts in volcanic output, solar intensity, or biological innovation have rewritten the planet's appearance before. Skies have changed color. Oceans have transformed their reflectivity. Entire surface expressions have been replaced without catastrophe, simply through persistent imbalance accumulating beyond recovery. What seemed permanent dissolved into something new. The present world fits this same pattern. Blue skies, blue oceans, and green continents feel definitive because they have endured across generations. Yet they depend on chemistry that can drift, on life that can evolve, and on energy that can vary. The planet makes no promise to preserve these conditions indefinitely. It continues to follow physical law, indifferent to familiarity. Understanding Earth as paused rather than complete reshapes perspective. It removes the expectation of finality and replaces it with continuity. The planet is not building toward a finished state, nor unraveling toward ruin by default. It is moving, always, through phases that last as long as balance allows. Each pause becomes a chapter, not an endpoint. This realization carries calm as much as it carries uncertainty. The same processes that altered past worlds operate slowly, giving life time to respond and adapt. Change unfolds over spans far longer than immediate experience. The illusion of completion arises because the pause is deep and steady, not because motion has ceased. Earth remains a process rather than a product. Its surface is a momentary expression of deeper systems in motion. Stability is real while it lasts, meaningful while it holds, but never guaranteed beyond the conditions that sustain it. The planet continues quietly, neither finished nor broken, simply balanced for now, waiting patiently for chemistry, life, and energy to drift once more into a different alignment. Human presence rests on a long delay, shaped by conditions that took immense time to assemble. Complex life depends on oxygen not simply for breath, but for the energy it makes available inside cells. This energy supports size, structure, movement, and the slow growth of intricate systems. Without abundant oxygen, life remains efficient but limited, bound to forms that function quietly and simply. Oxygen itself was not a gentle gift. Its arrival reshaped the planet through disruption rather than smooth transition. When it accumulated, entire ecosystems collapsed, unable to survive its reactive nature. Ancient life that had flourished for vast spans vanished from open environments. Their disappearance did not result from failure, but from success elsewhere. Oxygen producing organisms altered the world so profoundly that earlier worlds could no longer persist. This sequence forms an uncomfortable truth. Human existence depends on endings. The conditions that support complex life emerged only after previous planetary states dissolved. Purple seas faded. Hazy skies thinned. Anaerobic ecosystems retreated or disappeared. Each change cleared space for something new, even as it erased what had been stable before. These transformations unfolded slowly enough to feel gentle from a geological distance, yet their impact was absolute. Life adapted where it could and vanished where it could not. The world reorganized itself repeatedly, exchanging one stable arrangement for another. Only after oxygen settled into persistence did the long path toward complexity truly open. Even then, time stretched onward. Multicellular life appeared cautiously, experimenting with form and function. Bodies learned to cooperate internally, cells specializing rather than existing alone. This required energy margins that only an oxygen-rich world could sustain. The delay was not hesitation, it was preparation enforced by chemistry and physics. Humans arrived late because the planet required completion of many prior cycles. Atmospheres had to stabilize, oceans had to clarify, light had to become predictable. Biological systems needed time to explore complexity without constant chemical stress. Each requirement rested on conditions built atop earlier extinctions. This layered history means no stable world exists alone. Each rests on the remains of worlds that ended. Modern landscapes appear tranquil, yet beneath them lie records of vanished ecosystems that once felt just as permanent. Every stable phase becomes the foundation for the next, whether through accumulation or replacement. Recognizing this lineage reframes arrival not as destiny, but as consequence. Humans did not emerge at the peak of a plan. They appeared within a window opened by loss, adaptation, and long patience. The planet made space by changing, not by preserving everything it created. This understanding carries neither guilt nor triumph. It offers context. Existence sits within continuity, shaped by forces larger than intent. Complex life stands on extinct worlds not because destruction was required, but because change continued. Earth does not choose its inhabitants. It responds to conditions, and those conditions shift until new forms become possible. Long before large bodies walked, swam, or breathed, microbes learned how to shape a planet. They did so without motion or voice, altering the world through chemistry repeated endlessly at microscopic scales. Molecule by molecule, they transformed air, water, and stone, building the conditions that later life would inherit. Their influence arrived quietly, but it reached everywhere. Through metabolism alone, microbes reworked the atmosphere. They released gases, removed others, and altered balances that determined how light moved through the sky. Oxygen accumulated because they produced it. Methane faded because they disrupted its cycles. Ozone formed because oxygen reached high altitudes. No mountain range or impact event matched the cumulative force of these invisible lives working without pause. The oceans changed alongside the air. Microbial communities regulated acidity, controlled mineral deposition, and governed nutrient flow. They shaped the clarity of water and the chemistry of the seafloor. Entire marine systems rose and fell according to their activity. Long before animals occupied the seas, microbes had already written its physical rules. This influence never ended. Microbes remain Earth's most abundant and adaptable life form. They occupy environments that large organisms cannot tolerate, thriving in heat, darkness, pressure, salt, and chemical extremes. They persist in the deep crust, the upper atmosphere, polar ice, and boiling vents. Where conditions exist, microbes arrive first and linger longest. Even now, planetary chemistry depends on them. Microbes control the cycling of carbon, nitrogen, sulfur, and oxygen. They regulate soil fertility, ocean productivity, and atmospheric composition. Forests grow only because microbial networks prepare the ground. Oceans remain alive because plankton maintain energy flow. Every breath connects back to processes microbes oversee continuously. Large life exists inside this system rather than above it. Animals and plants function as extensions of microbial networks, not replacements for them. Cells rely on ancient biochemical machinery, perfected by microbes long before multicellular bodies appeared. Even complex organisms host vast microbial communities within themselves, systems essential for digestion, immunity, and development. No large life exists independently. This hierarchy reshapes how dominance is understood. Size does not determine influence. Visibility does not equal control. The most transformative life on Earth operates beyond direct perception. Microbes do not adapt to planetary conditions, they generate them. The world adjusts around their chemistry, not the reverse. Across Earth's history, every major transition traces back to microbial activity. Purple seas, oxygenated skies, blue oceans, and stable climates all emerged from microbial processes layered across time. Each planetary phase rested on their quiet persistence. Seen from this perspective, the planet remains a microbial world. Large organisms decorate the surface briefly, adding complexity and movement, but the foundation never changes. Microbes continue their work steadily, reshaping chemistry at scales too small to notice and too large to escape. Earth moves forward within the system they built and still maintain, molecule by molecule, moment by moment. Color draws the eye, but it does not tell the whole story. Skies and seas announce the present state of the planet, offering a visible summary of conditions at the surface. Yet beneath those hues, deeper processes continue unchanged by appearance. What can be seen reflects balance, not origin. The true motion of Earth unfolds below the colors, steady and persistent. Under continents and oceans, ancient chemistry still circulates. Elements move through rock, water, and heat along pathways established billions of years ago. Carbon sinks into sediment and rises again through volcanic breath. Sulfur cycles between mineral and gas. Iron shifts states in darkness, indifferent to the life above. These reactions do not pause when new colors emerge. They proceed quietly, carrying forward rules older than any sky. The oceans hold similar continuity. Beneath plankton-rich surfaces and blue reflections, chemical gradients persist that resemble those of earlier worlds. In deeper waters and sediments, oxygen fades and ancient metabolisms continue their work. Microbes process compounds the same way their ancestors once did, maintaining cycles that predate complex life. Modern ecosystems depend on these processes even when they no longer resemble them. The atmosphere, too, carries memory. While its composition has changed, the mechanisms that govern it remain familiar. Gases mix, react, and disperse according to the same physical laws that shaped hazy skies long ago. Ozone filters light now, but radiation still drives chemistry above. Balance holds because feedback aligns, not because the system has been replaced. This continuity gives the planet depth beyond its surface. The past was not erased to make room for the present, it was layered beneath it, absorbed into ongoing motion. Ancient reactions became foundations rather than relics. What once dominated now supports quietly, hidden but essential. Life mirrors this structure. Modern organisms rely on biochemical pathways refined long before bodies grew large. Cellular machinery traces back to microbes that thrived under different skies. Even complex life carries internal echoes of earlier Earth, operating through inherited chemistry that has never stopped running. Evolution added structure, not new rules. Seen this way, the planet resembles a palimpsest rather than a clean page. New expressions are written over older ones, but the underlying text remains legible to those who look closely. The colors of today do not replace the chemistry of yesterday, they rest upon it. Understanding Earth beneath the colors dissolves the idea of separation between eras. The purple seas, the blue oceans, the green continents all belong to one continuous system. The past persists, not as memory alone, but as active process. It shapes the present invisibly, sustaining the conditions that allow current forms to exist. The surface may change its palette, but the planet's deeper rhythm endures. Color comes and goes, chemistry remains. Earth carries its history forward, not through display, but through motion that never truly stops. To see Earth without human expectation requires a quiet subtraction. Blue is removed first, lifted away from the assumption that skies must carry it. Green follows, released from the comfort it offers as a signal of life. As these familiar colors fall back into neutrality, the planet loosens its personal shape. What remains is not absence, but clarity. Without those anchors, Earth is no longer framed as a backdrop for human presence. It becomes a system moving through states, guided by chemistry, energy, and time. Skies are no longer judged by brightness, oceans by color, or land by familiarity. They are understood as outcomes, momentary alignments formed by deeper processes still unfolding beneath them. This shift changes how stability is perceived. Familiar hues no longer suggest permanence. They suggest equilibrium, held temporarily within narrow boundaries. A blue sky is read not as normal, but as specific. A green surface is seen not as essential, but as conditional. The planet's appearance becomes legible as a balance sheet rather than a promise. As expectation fades, attention moves inward. Subsurface chemistry, atmospheric circulation, and biological feedback come into focus. The quiet work of microbes, minerals, and light replaces surface impressions. Earth feels less like a place that belongs to its current inhabitants and more like a process that hosts them briefly. This does not diminish meaning, it reframes it. Detached from comfort, the planet reveals patience. Changes that once felt unsettling soften into continuity. Purple seas, hazy skies, blue oceans, and green continents all belong to the same motion. Each phase feels complete while it lasts because balance supports it, not because it represents a final state. Recognizing this removes the pressure to defend the present as ideal. This perspective carries calm rather than detachment. By releasing expectation, understanding expands. The planet no longer feels fragile because it no longer feels fixed. It has endured many forms without losing coherence. Change becomes evidence of resilience rather than threat. The system adapts because it must, and it does so slowly enough to remain intelligible. Seen this way, Earth is generous but impartial. It provides conditions where alignment allows, withdraws them when balance shifts, and never pauses its deeper motion. This rhythm does not require familiarity to function. It requires only adherence to physical law and time enough for patterns to settle. Letting go of blue and green allows appreciation of structure beneath appearance. The planet becomes readable without preference. Its past and present align into one continuous process, unfolding calmly across deep time. In that understanding, comfort no longer depends on permanence. It rests in coherence. Earth does not need to look like home to remain meaningful. When expectation dissolves, the planet becomes larger, older, and quieter. Understanding replaces attachment, and with it arrives a deeper calm, shaped not by reassurance, but by perspective. Earth's history suggests that change is not an exception, but a capacity held in reserve. Chemistry does not settle permanently, even when balance feels complete. The same forces that once thinned hazy skies, oxygenated oceans, and shifted surface colors continue to operate quietly. Given enough time, alignment can loosen, and new arrangements can emerge without ceremony. Future chemistry could drift through many paths. Volcanic cycles may alter atmospheric composition slowly. Continental movement can reshape circulation and climate. Biological innovation may redirect elemental flows in subtle ways. None of these processes require catastrophe to unfold. They accumulate patiently, adjusting ratios and feedback until the planet expresses itself differently at the surface. With new chemistry comes the possibility of new color. Changes in atmospheric scattering could tint the sky in unfamiliar ways. Altered ocean chemistry might shift reflectivity away from blue. Surface biology could adopt pigments better suited to future light conditions. These changes would not announce themselves as departures from normal. They would feel normal once established, just as earlier worlds did in their time. Stability, when viewed across deep time, reveals itself as conditional. It holds only while opposing influences remain balanced closely enough. When that balance shifts, even slightly, the surface responds. Earth has never required permission to change its appearance. It moves according to physical law, not expectation. Familiarity offers no protection against rearrangement. This does not imply imminent transformation, nor does it diminish the present. It places it within context. The current world exists because conditions support it now. That support could persist for immense spans, long enough for future beings to regard this state as permanent. Yet history shows that permanence is always provisional. Considering how many Earths are possible requires releasing the idea of a single trajectory. The planet does not progress toward one ideal form. It explores what is stable under shifting constraints. Each stable configuration becomes a complete world, inhabited fully and coherently until conditions drift again. Purple seas, blue oceans, and green continents are examples, not limits. The number of possible Earths is therefore not fixed. It expands with chemistry, biology, and time. Some configurations may never arise. Others may emerge briefly or endure for ages. What matters is not the count, but the principle. The planet retains the capacity to become something else while remaining itself. Earth has changed before without asking permission, because no permission exists to be granted. There is only balance and consequence. Understanding this does not demand unease. It offers perspective. The present world gains depth when seen as one expression among many, shaped by alignment rather than destiny. In that light, the future is neither fragile nor secure. It is open. Earth will continue to respond to the forces acting upon it, assembling and dissolving worlds as chemistry allows. The surface will reflect those changes honestly, in color and form, just as it always has, carrying forward the quiet truth that appearance follows balance, and balance is never final. Earth has worn many faces across its long history, each one complete while it lasted. Skies have shifted in tone, seas have carried unfamiliar colors, and surfaces have reflected life very different from what exists now. None of those worlds were unfinished. They were balanced expressions of chemistry and time, held gently in place until balance moved on. The present Earth belongs to this same lineage. Blue skies and blue oceans feel intimate because they surround daily life. Green landscapes feel reassuring because they signal stability and abundance. These features are temporary, but they are not illusions. They are real states, assembled patiently by processes that align just long enough for them to feel permanent within a lifetime. Tonight, the planet rests inside this arrangement. Oceans circulate calmly, skies scatter light in familiar ways, and living systems exchange gases and energy with quiet efficiency. Nothing about this moment is incomplete. It exists fully, supported by countless interactions beneath the surface and above it, each doing its part to sustain the current phase. At the same time, nothing is fixed. The forces that shaped earlier worlds continue without pause. Chemistry flows through rock and water. Energy moves between sun, atmosphere, and surface. Life adapts constantly at scales too small to notice. These motions do not hurry. They wait, adjusting slowly, allowing balance to hold until it no longer can. This waiting gives the planet its calm. Change is not dramatic by default. It arrives gently through accumulation rather than interruption. Whole worlds fade not in moments, but across spans so long that each generation experiences only continuity. By the time transformation becomes clear, it already belongs to history. Understanding Earth as resting between worlds softens the idea of ending. When one phase yields to another, nothing is lost entirely. The next state carries forward elements of what came before, reshaped but recognizable in chemistry and process. Purple seas did not vanish without legacy. They helped prepare the conditions that allowed blue oceans to exist. Each world leaves traces woven into the next. This perspective offers a quiet form of reassurance. The temporary nature of the present does not diminish its value, it highlights it. Moments of balance are precious precisely because they do not last forever. They are invitations to observe, understand, and appreciate the alignment while it holds. Earth does not rush away from the present, nor does it cling to it. The planet rests here because forces agree for now. When that agreement shifts, it will rest somewhere else just as calmly. Change will come, as it always has, without urgency or intent. For now, the world breathes steadily under a familiar sky. Oceans reflect light they did not always carry. Life thrives within conditions shaped over immense time. This phase is one among many, held gently in the flow of deep history. The planet waits, balanced and quiet, between worlds, carrying its past forward while remaining exactly where it is tonight.